The single most important law in this chapter is the so-called Ohm's law. It is one of the most elegant laws in all of physics because of simplicity in form and because of its great range of applicability. We know that without an external electric field, in a piece of metal there will be no current. Okay, you have to put it in the electric field, and that's how you produce a current. And the current is caused by the electric field. Is there a connection between the current density J and the electric field E in a certain region? Well, this is addressed by what's called Ohm's law. And to understand Ohm's law, we look at the microscopic aspect of the motion of these drifting electrons. Let's say I have an electron starting from here. Okay, let's imagine what happens to that electron as time goes by. Okay, now it has a random motion velocity even without the electric field. So it's just going to move randomly back and forth, back and forth, back and forth. But overall, after a certain period of time, would you predict that it's going to go somewhere here or somewhere there with certainty? Of course not, because it has an equal probability of going to the right and going to the left, going up or going down, right? So it just moves around back and forth, but it's not going anywhere. It's not drifting anywhere. On the other hand, once you have an electric field, let's say the electric field points from right to the left. Okay, this being a negative charge, it's going to start to develop a drifting velocity that way. It's a tiny velocity compared with random motion velocity, but that velocity always points this way, and therefore it's going to create a net motion of the electron. The electron is no longer just doing random motion. I mean, still do random motion, but on top of that, you find that over time, it drifts. It doesn't just move randomly, it drifts along that direction against the direction of the electric field, being negatively charged. So that is why we call it drift velocity. Okay, now, without random motion, the electron will simply form a straight line, right? It's just going to move in a straight line. It will be accelerated uniformly. Now, wouldn't that be nice? But in reality, the motion of the electron is pretty much made of straight line segments, say between here and there. It starts from here, and it pretty much moves in a straight line at a very, very high speed, which is the random motion speed, even though there's a tiny drift speed that you add to that. But once it hits here, what happens? How come it abruptly turns into a different direction? What's going on here? Yeah, it made a collision with somebody else, right? It's punctuated by frequent collisions. We're talking about billions of collisions per second. Okay, so even though the electron moves very fast, this is a short segment because it's frequently punctuated by collision. So after a collision, the collision is random, and therefore after the collision, on average, the electron pretty much had to start anew. It has lost its memory. It didn't remember how fast it was moving before because the collision is random. So say it goes that way, okay? And between here and there, again, it's mostly random motion velocity, but the electric field will accelerate a little bit. But by the time it reaches here, once again, it has a new collision and forgot about what happened to it before, so it starts anew. Okay, so you have these segments. But overall, the electron will slowly drift backwards, opposite to the electric field. Now, let's look at a typical segment. Okay, a typical segment between here and there. I don't care about the random motion because it doesn't produce any electrical current. I'm interested in the drift velocity. In order to find J, I need to find drift velocity. Okay, look at here. I need to find drift velocity. Q, which is E in our case, and Vd. All right, I need to find Vd. Now we got to understand that Vd is different for different electrons. Some electrons may, if you're lucky, you go from here to there for a long distance without any collision, and there is more time then for the electric field to build a greater drift velocity. And some electrons will suffer a collision immediately after the previous one, and therefore it will not have time to develop a large value of Vd. But anyhow, we need to know the average value, okay, the mean value of Vd. That's what we're interested in. So let's say we have a collision here, and then let's look at what happens between this collision and the next collision. Okay, again, let's forget about the random motion. Let's just consider the organized motion due to the electric field. Right after the electron emerges from this collision, on average, how fast? On average, what is the drift velocity at that moment? Well, remember, the collision is very violent and very random, and therefore it can move in every possible direction, right? So on average, it has been knocked totally out of its previous memory. There is nothing left, and therefore the initial velocity Vd is 0 when it just emerges out of the collision. Okay, now from here to there is a short period of time in which the electron is subject to a uniform, more or less uniform electric field. It's uniform because this distance is very short. Okay, it will be accelerated by what kind of acceleration? A is equal to the force exerted on the electron divided by the electronic charge. Okay, and what is the force exerted on the electron? I'm sorry, divided by its mass. Okay, and what is the force exerted on the electron? That would be the electronic charge E, actually negative E, E being the magnitude of the electronic charge, 1.6 times 10 to the negative 19 coulomb. So it's negative E times the electric field E. Okay, that is the electric field responsible for creating the current, external electric field. We divide it by its mass. Okay, and this acceleration is more or less uniform because the electric field between here and there is more or less uniform. Now, how long does it take to go from here to there? That will be the time duration in which such an acceleration is available to this electron to accelerate it, right? And again, that time interval varies. Even for the same electron, it can get longer time and shorter time, longer time, and so on. So what we need to know is to find the average time. Okay, the average time between two collisions. Don't worry about how to calculate it, but there is a way to do that which is out of the scope of this textbook. But let's say the time it takes on average for the electron to move between one collision and the next collision is tau. Okay, then this is the time interval that is available for the electron to let it accelerate under such a force, under such an acceleration. Therefore, after this much time, it's going to move at this velocity. Okay, on average. Tau is already the average value, therefore Vd is the average value over all these electrons. See? A times tau. Okay, and that is negative E tau over m times the electric field. Right? I'm just copying this to here. Now, once we know Vd, what is J? J equals to, go back to the first page, Q and Vd. Q is negative E in our case, the charge carried by each electron. Negative E n Vd. I now know what Vd is. Vd is right here. So it's negative En times a negative sign, another negative sign that cancels out, E tau over m times the electric field. Now we can rewrite this as J equals sigma E, okay? And here sigma is not the surface charge density, rather it is this guy. Okay, sigma is in our case E squared times n times tau over m. This is the expression for this constant sigma. And what is the meaning of sigma? Sigma is called electrical conductivity, or sometimes simply called conductivity. Conductivity. And it is equal to this expression, n E squared tau over m. Regardless of the expression for sigma, which we already obtained, even if you didn't know that, as long as you do know that J equals a constant times the local electric field, that is already something very, very important. That, in fact, is the local version of Ohm's law. By local, I mean from point to point. At this point, I have the electric field E. So at that point, at that same point, what is the resulting current density? Is a constant sigma times E, and that sigma is the local value of the electrical conductivity. Now, the greater the value of sigma, the greater the electric field, the greater the electrical current density produced by the same electric field. Okay, so you can imagine conductors will have larger values of conductivity because for the same electric field they can produce a greater current. Okay, and we derived the expression for sigma. This is based on our understanding microscopically, and this in fact is only a simplified model of what's really going on in a piece of metal, and we have a name for it. We call it Drude's model. It's named after Drude. Joule's model. Okay, and of course, in order to calculate sigma numerically, we have to know what n is, we have to know what tau is, which is the most difficult part of the calculation. But let's not deal with that. Okay, all we have to understand now is that J indeed equals sigma times E. Sigma is whatever, however you calculate, it's called conductivity. Okay, some of you may have some good knowledge about Ohm's law before, but it very likely was different from what we learned here. You probably learned something called V equals IR, remember that? Okay, but we can show easily that this is equivalent to this version. V equals IR, what does that mean? Well, it's another way of writing down Ohm's law, but it's not a local formula. Rather, it extends the application of Ohm's law over a certain range. Okay, let me explain to you. Suppose I have a piece of metal or whatever material, a piece of metal. It's got a uniform cross-sectional area A, and it's got length L. Okay, length L. Now, I wish to establish an electric field in its region, so therefore establishing a current. And the way I can do that is by hooking up to a battery. That's one of the most common ways to do that. I hook up to a battery like this. This battery supplies a voltage difference V. Okay. As a result, the current will flow from the positive to the negative terminal. Right? The voltage difference between this end and that end of this piece of conductor is V. Now, for simplicity, assume the electric field is uniform. Okay, in between this terminal and that terminal. If the electric field is uniform, then over distance L, what kind of voltage difference would it create? Well, it's clear that V is E times L, right? V equals E times L. Now, if we know what V is, we know what L is, we can find E, which is V over L. But on the other hand, E, once you know E, you can also get the current density, right? It's just sigma times E. So therefore, we can write further E as, because J equals sigma E, right? I can further write E as J over sigma. So it's J over sigma times L. But usually we don't measure J, rather we measure the total amount of current. We'll put a meter here, we'll put what's called an ammeter here. We can measure total current instead of current density. So the total current over this cross-section area is I, and I over A will get you J, right? Divided by sigma times L. Now, let's rewrite this a little bit, something we can recognize more easily. This V equals I, which is this I, times 1 over sigma L over A. Right? Now, sigma is a constant if it's a uniform material. L is the length and A is the cross-section area. So this whole thing here is really a constant, which I call R. What's R called? R, as you probably know, many people know that, it's called electrical resistance of this piece. In other words, for shorthand, we just simply call it resistance. Okay, resistance. And therefore, V equals I times R. This is the great Ohm's law. In a more familiar expression, Ohm's law. Okay, this is used more often than J equals sigma E, because it's not very easy to measure E and J locally, but rather, V can be measured with a voltmeter and I can be measured with an ammeter. So this V equals IR is something that we apply to real electrical circuits. It's got an incredibly simple form. Okay, V and I are linearly proportional to each other for many materials, and that all we have to do is find R. R is called the resistance, and by the way, as you probably know, the SI unit of R is what? Is ohm, right? Which is named after Ohm, who discovered the law. And so what's 1 ohm equivalent to? 1 volt over 1 amp. So 1 ohm is equal to 1 volt over 1 amp. And usually we use the first letter. Say amp, we use the capital A, but here the capital O is a little bit could be a little bit misleading, because it could be mistaken as a 0, and therefore we borrow the Greek letter omega. Okay, And when we say 1 ohm, we use the symbol capital omega, but we do not read this as omega in this context. We read 1 ohm. Okay, so this large omega means ohm. So that is the famous Ohm's law. If you take a closer look at the expression for R, you copy this. R equals what? 1 over sigma L over A. Okay. The greater the value of sigma, the smaller the value of R. They are reciprocals of, they are inversely proportional to each other. Now, sigma is called conductivity. Okay, imagine if if a material has a very large value of conductivity, that means it's an excellent conductor, right? If it's an excellent conductor, shouldn't it have smaller resistance? So R will be smaller. That makes sense. Okay, so it makes sense that R is inversely proportional to sigma, not proportional to. And we define 1 over sigma as rho. That's the definition. Sigma is called conductivity. What do you think rho is called? Resistivity. Okay, that makes sense. Resistivity. So we can write this as rho L over A. What is the meaning of rho? Well, rho would be equal to R if L is equal to 1 unit and A equals 1 unit. So what is rho? Rho really is the resistance of a certain type of material with unit length and unit cross-sectional area. Okay, that's called resistivity, and and it's a direct reciprocal of conductivity. Okay, so this formula also tells us that given a material of a certain resistivity, the longer it is and the smaller its cross-sectional area, the greater its resistance. Does that make sense? Okay, does that make sense? Well, think of, okay, if I make this thing twice as long, keeping everything else the same cross-section area, hook up to the same battery, but it's twice as long. Now, if it's twice as long, then the same voltage difference will have to be applied over a region twice as long, and therefore it's only going to cause an electric field that's half as much, right? Because L doubles, V is the same, and that will produce only half the current density and therefore half the current. So the longer the Y is, the greater resistance. That makes perfect sense. Now, what about the cross-section area? It says here that if you double the cross-section area, you get half the resistance. In other words, a fatter cross-section area make the current flow with greater efficiency. Okay, you produce a greater current with the same voltage. Does that make sense? Well, that also makes sense because you can think of it as, you know, as what happens on a freeway, right? I mean, if everything else is the same, if you're driving on congested freeway, if all of a sudden somebody opens up another lane, how does that affect the traffic? Does it make traffic easier or harder? Well, of course it makes it easier because now the current can not only flow this way, can also flow, in a parallel lane, and therefore it's going to ease the congestion. The electrons will collide less with each other because they got more places to go, and therefore you can make the current greater. So it also makes sense, okay, qualitatively, that R is proportional length of the resistor and inversely proportional to the cross-sectional area of the resistor. And by the way, by resistor I mean it's just, you know, a material shape that we form a certain shape, okay, form this material into a certain shape so that when you apply a voltage difference across its two ends, a certain amount of current flows through it, such that V equals IR, and R is its resistance, and this object is called a resistor. Usually we use conducting materials to make resistors in a real electrical circuit.